Good morning, all of you. So we are discussing the carbon family. In the carbon family, the last part of that is silicates we are discussing. So yesterday we started what are silicates and what are the types of silicates are present. So once again, we just briefly discuss what are silicates and the types of silicates. Thereafter we will continue. Okay, silicates. So silicates are nothing but these are the minerals which are having silicon and oxygen in the form of SiO4 minus 4 tetrahedral units in different patterns. Okay, that minerals we call it as what? Silicates. And based upon the linkage of these tetrahedral units, based upon the arrangement of these tetrahedral units, we are classifying the silicates into many types. So in that, the first one we already discussed. The first one is what? Orthosilicates. Orthosilicates also we call it as what? Nesosilicates. And their general formula is what? SiO4 minus 4. Okay, SiO4 minus 4. So that is a general formula of orthosilicates. What are orthosilicates? Orthosilicates, these are the simplest silicates having a single discrete tetrahedral unit. It has only one tetrahedral unit and there was no sharing of oxygen atoms. There was no sharing of oxygens with any other units. Why? Because there was only one tetrahedral unit, so there was no chance to share oxygen with any others. So best example for orthosilicates is what? olivine and phenacite. So those are the two minerals which are examples for orthosilicates. And if you see the structure of silicates, orthosilicates, so SiO minus, O minus, O minus, O minus. So if we connect these four edges, we will get a tetrahedral structure. So this is a general structure, and the same we represent with so in this form also. Here at the center, here silicon is there. Okay, in here one silicon and one oxygen towards the viewer, 3 oxygens at 3 vertices of the triangle. So this is another representation. We commonly use this representation to show the large silicates. Okay, so this is the first one, that is orthosilicate. Next one, pyrosilicate. Pyrosilicate also we call it as sorosilicates, and its general formula is what? Si2O7 minus 6. Si2O7 minus 6. Total here, these silicates are formed by linking 2 tetrahedral units. So by linking 2 SiO4 minus 4 units, okay, by sharing one oxygen atom at one corner. So these are formed by linking of 2 SiO4 minus 4 units by sharing one oxygen atom at one corner. So this is pyrosilicates. And example, thortivetite, and this formula is Si2O7 scandium complex with the silicates. And if you see the structure, so these are the 2 tetrahedral units which are sharing one oxygen atom. If the oxygen atom is shared by 2 tetrahedral units, there was no charge. Here the charge will be only these 3 oxygens and these 3 oxygens. Total 7 oxygens but out of 7 only 6 are having -1 charges. So that is why Si2O7 -6 charge only they are having. So this is a general formula about the pyrosilicates. And the next third one, cyclic silicates. And these cyclic silicates also we call it as ring silicates. Why? Because these silicates, by joining, they forms ring-like structures, so called ring silicates. But there was a condition to form these ring silicates, that is, the number of tetrahedral units should be minimum of 3. If the silicate units are less than 3, they will not form the ring silicates. So these silicates are formed by linking or by joining 3 or more SiO4 -4 units. So by linking 3 or more than 3 silicate units cyclically, in cyclic manner, they forms this cyclic structure or ring silicates. Now, okay, they're forming by linking 3 or more than 3. Then how many of oxygens are shared by each tetrahedral unit? So as like here only one oxygen atom is sharing, but in cyclic silicates each tetrahedral unit shares 2 oxygen atoms at 2 corners with different unit cells, different units. So if you see the structure, this is one tetrahedral unit, this is another one, and this is another one. So total 3 tetrahedral units, and each tetrahedral unit is sharing 2 oxygens. Here these 2 corners are sharing. This corner is sharing with this tetrahedral unit. This corner is sharing with this tetrahedral unit. Overall, each tetrahedral unit is sharing how many of oxygens? 2 oxygens are sharing. And if you see the general formula, what is the general formula of this cyclic silicates? That is SiO3N -2N. SiO3N -2N. Suppose if there was one silicon atom, so what is the charge here? -2 charge will be. If 2 silicon atoms are there, -4. Let us see. Suppose I told you already, if the oxygen atom is sharing, okay, then there was no charge on the oxygen atom. So here, if you take this tetrahedral unit, here there was no charge, here also there was no charge. But these 2 oxygens are not sharing with any others. So that is why here minus charge, here minus charge. So one tetrahedral unit if you take, what is the total charge belongs to that particular unit cell? Only -1 and -1, that is -2. So each tetrahedral unit is having -2 charge individually. So that is why general empirical formula to show this cyclic silicates is SiO3N, and you may get that out. Why SiO3? SiO4 now. But see, if you take this sharing oxygen, this oxygen atom is shared by 2 tetrahedral unit. That means this out of this, how much part belongs to only particular one unit cell? Only half. So half oxygen belongs to this tetrahedral unit, half belongs to this tetrahedral unit. Similarly here also, this oxygen half belongs to this, half belongs to this. So overall 1 plus 1, 2, half plus half, 1, 2 plus 1, total 3. So that is why each tetrahedral unit is having only 3 oxygen atom belongs to particular one unit. Okay, so that is why SiO3N -2N is the general formula for cyclic silicates. Best example for the cyclic silicate is what? Beryl. Beryl. So what is the formula for the beryl? Be3Al2SiO3 SiO3 6. Total 6 silicon atoms are there. So definitely here charge will be -12. To compensate this -12, the total positive charge should be +12. See that beryllium belongs to second A group element, so it has +2. +2 into 3 +6. And aluminium third A group +3 into 2 +6. Total overall positive charge is +2. So that is why it's a neutral. So this is about the cyclic silicates. So they may ask you the question, in cyclic silicates, how many of oxygen atoms are sharing by each tetrahedral unit? How many? 2 oxygen atoms are sharing. Okay, so this is about the cyclic silicates. Next, inosilicates. Inosilicates. So till now, based upon the what number of oxygen atoms sharing. See that in the first orthosilicates, if you see, in orthosilicates there was no oxygens are sharing. Whereas in pyrosilicates, 1 oxygen atom is sharing by each tetrahedral unit. Whereas in cyclic silicates, 2 oxygen atoms are sharing by each tetrahedral unit. Whereas in inosilicates, okay, if each tetrahedral unit sharing 2 or more than 2 oxygen atoms, okay, then those silicates we call it as what? Inosilicates. So how we are defining these inosilicates? These are nothing but, these are formed, the inosilicates are formed by linking or by joining many SiO4 minus 4 units, by joining many number of silicate units only, but many number of silicate units, and sharing 2 or more oxygen atoms with others. Okay, so these silicates are formed by many number of silicate units and they are sharing 2 or more than 2. You may get the doubt. Then here also 2 oxygen atoms are sharing. Then why don't we call these cyclic silicates as inosilicates? Okay, here the difference between cyclic silicates and inosilicates are, here they are cyclically linking, but in inosilicates they are not cyclic. Okay, they are linear or a double chain. So that is a difference between cyclic and inosilicates. Okay, now come to the point. And these inosilicates, we are in these inosilicates mainly 2 types are there. 1, 2. The one is what? Linear silicates. Linear silicates. Linear silicates also we call it as pyroxenes. Okay. Linear silicates also we call it as what? Pyroxenes. Whereas the second one, double chain silicates. Double chain silicates, and the double chain silicates we call it as amphiboles. Amphiboles. So remember the other names also. Why? Because sometimes in the questioning they may use this alternate name of the particular silicate also. So for every silicate you should remember its main original name, their alternate name, and their general formula and examples. From the silicates, this kind of questions only they'll ask probably. Okay, let us discuss the first one, linear silicates. Linear silicates. Okay, the first one in inosilicates is linear silicates or linear chain silicates, also we call it as pyroxenes. Now the general formula of these linear silicates is same as like cyclic silicates. So that is what? The general form is SiO3 N minus 2N. The general formula of linear silicates and cyclic silicates both are same. Here these linear silicates are formed. These are formed by linking or by joining many number of silicate units, linearly. Understood the difference between them? Here there are also many number of silicate units cyclically, so called cyclic silicates. Here many number of silicate units are linking linearly. Okay, so that silicates we call it as what? Linear silicates. Okay, they are formed by linking many number. And how many of oxygens are they sharing? See, each tetrahedral unit sharing 2 oxygen atoms. Two oxygen atoms with others. With others, if you see, so best representation. How many tetrahedral units? 1, 2, 3. 3 tetrahedral unit. Okay, 1 tetrahedral unit. Second one. Third one. So likewise it will polymerize linearly in both ways, in right hand side and as well as left hand side. And if you see anyone, see, if you take this one, you may get the doubt, only one oxygen atom is sharing. You don't think that here left side also few silicate units are there. I am not drawing that one. So you take this one. So the repeating unit here is this one. This is the repeating unit. So in this repeating unit, you tell me how many of oxygen atoms belongs to one particular unit cell. So if you take this one, this oxygen belongs to this one. The central oxygen also belongs to the same. And out of these two oxygens, in this oxygen if you see, half part belongs to this one, half part belongs to this one. Similarly, this oxygen also, half belongs to that one, half belongs to this one. So overall, how many oxygens per each unit cell? Only 3. 1 plus 1, half plus half. Total 3. That is why SiO3. Okay, and what is the charge? I told you there was no charge here, there was no charge here. Why? Because these two oxygens are sharing. If oxygen is sharing with others, there was no charge on it. That is why -2. So if N silicate units are there, then it has -2N charge on it. That is why SiO3N -2N. So the general formula of linear silicates and cyclic silicates both are same. Okay, coming to the example for this. Example for linear silicates is spodumene. Spodumene. Okay, and LiAl SiO3 twice. Lithium +1, aluminium +3. Total overall positive charge is +4. Overall positive charge is +4. SiO3, each one is having -2. How many silicates are there? 2. 2 into -2, -4. Neutral. So lithium aluminium silane or silicate is an example for, is a general formula of spodumene. So in linear silicate, each silicate unit is sharing how many of oxygen atom? 2 oxygen atoms. Remember that. Next, move on to the next second kind of ionosilicates is double chain silicates. Double chain silicates. So the double chain silicates also we call it as what? Amphiboles. Amphiboles. And if you see the general formula of this double chain silicates, that is Si4O11N -6N. Si4O11N, suppose if N repeating units are there, then what is the charge on it? -6N charge will be there. So this is the general form, very very important. So if you draw the structure, you will get an idea about it. So first I am drawing structure of double chain silicates. So this is a single chain silicate. So this is a single chain silicate. If you take two this kind of silicates, if you join them, then it is double chain silicates. Here I am drawing, let us see carefully. See that this is one. So likewise it will continue, it is not stopping. So this layer, this is one chain silicate, this is another chain silicate. So total how many of chain silicates are there? 1 and 2. This is number 1, this is number 2. Total two chains are again sharing some oxygen atoms. So total 2 chains are present, that is why we are calling this as double chain silicates. And if you see this double chain silicate clearly, how many of oxygens are sharing by each tetrahedral unit? See, if you take this tetrahedral unit, let us take this one I am taking. You tell me after seeing this structure, this oxygen is sharing and this oxygen is also sharing. That means how many of oxygens are sharing by each tetrahedral unit? 2. Now you take any of these intermediate tetrahedral unit, either this one or this one. Okay. Suppose if you take this oxygen, this tetrahedral unit, tell me how many of oxygens are sharing. This oxygen is sharing with this tetrahedral unit. This oxygen is sharing with a neighboring tetrahedral unit. This is also sharing with this one. So total 3 oxygen atoms are sharing by tetrahedral unit, each tetrahedral unit. So here 2 types of tetrahedral units are present in double chain silicates. So one kind is what? The tetrahedral units which are sharing only 2 vertices. 2 vertices means 2 oxygens. And the tetrahedral units which are sharing 3 oxygen atoms. Okay, so in double chain silicates, there was two kinds of tetrahedral units. Okay, what are those? So one is sharing 2 oxygen atoms. Another one is sharing 3 oxygen atoms. Sharing 2 oxygen atoms, sharing 3 oxygen atoms. So all terminal tetrahedral units are sharing 2 oxygens. You take this one, sharing 2. This one also sharing 2. So all terminal tetrahedral units are what? External tetrahedral units are sharing 2 oxygens. Internal tetrahedral units are sharing 3 oxygens. All these internal tetrahedral units are 3 vertices, so they are sharing. All external tetrahedral units are sharing only 2 oxygen atoms. So if you look at the structure, you can observe. Coming to what is a monomeric unit here? Monomeric unit. So the 2 internal tetrahedral units and 2 external tetrahedral units. So you should take this from where to where. I am taking from here to here. So this as a monomeric unit I am taking. Why? Because again from here, again same thing will repeat. Understood? So this is the monomeric unit in this double chain silicate. So if you take this as a monomeric unit, in these monomeric units, how many of silicon atoms are there? So here one silicon atom, here second one, here third one, and here fourth one. Right? Total how many of silicon atoms are there? 4. So that is why Si4. Now count the number of oxygens. See, this is sharing, so half. This is also sharing, half. So here half, here half. 1, 2, 3, 4, 5, 6, next 7, 8, 9, 10. I think we missed this 2, I think. Once again we will count. Here half, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up to here complete. Next these oxygens are half part is sharing by this. So here half and here half. Total up to here 10 and this is 1. Total 11 oxygens belongs to one monomeric unit. That is why Si4O11. Now, what about the charges? Okay, so if you take one monomeric unit, what are the oxygens which are not sharing? This is not sharing. So 1, 2, and then 3, 4, and this is also not sharing, and this is also not sharing. Total -6 charge. So that is why the general formula of double chain silicate is -6n. So this is about the double chain silicates. What is the best example for double chain silicates? Asbestos. Asbestos is the best example for double chain silicates. And if you see the features or the characteristics of this asbestos, this is a fibrous silicate, and also it is a non-combustible silicate. It is a non-combustible silicate. So because of its non-combustible nature, okay, we can use this asbestos as what? Thermal insulating material. Thermal insulating material, and also for brake lining, for lining of brakes, and also for sealants, we can use this asbestos. But remember that the usage of asbestos is restricted because it is a carcinogenic in nature. Because of its carcinogenic means cancer causing. So if we expose to this asbestos for a longer days, okay, then that person may affected by the cancer. So that is why, because of its carcinogenic nature, the usage of asbestos nowadays is restricted. So this is about the asbestos. Okay, double chain silicates. With this, ionosilicates have been finished. Next type of silicate is sheet silicates. Sheet silicates. The sheet silicates is also, we call it as phyllo sheets. Okay, that's not a matter. So sheet silicates, come to the sheet silicates. These silicates are formed by joining many number of silicate units by sharing 3 oxygen atoms. Okay, by sharing, each tetrahedral unit is sharing how many of oxygen atom? 3 oxygen atoms are sharing with other unit cells, so that we are getting a network sheet-like structure. Network sheet-like or layered-like. Network layered-like structure, as like graphite, one layer, another layer. Likewise, so these tetrahedral units, they form a layer-like structure. Okay, and layer one upon another layer, and another layer upon second layer. Likewise, what? All layers arrange one upon other. Okay, so layer by layer structure will be present, and between these layers there was a very weak van der Waals forces. Van der Waals forces exist between layers. So these features are same as like graphite. Even in the graphite also, between the layers, okay, there is a very weak van der Waals forces. Because of the weak van der Waals forces, one layer can easily slide over another layer, so that we are using graphite as a lubricant. Same as like here also. So they are existing like layer by layer, and between the layers very weak van der Waals forces. So we can also use this as a lubricant, okay, alternate for graphite. So this is about sheet silicates. Okay, example for this sheet silicate is talc and mica. Talc and mica, these are the examples for sheet silicates. Next, and coming to the, and when you may get the, what is the general formula for sheet silicates? So if you see the general formula, Si2O5N minus 2N. Si2O5N minus 2N. So the structure is like what? Network like structure. So it's not easy to draw this structure here. You just go through the textbook once. You can easily understand. Next one, the last one, three-dimensional silicates. Three-dimensional silicates, also we call it as what? Tectosilicates. Tectosilicates. And what about the three-dimensional silicates general formula, that is SiO2N. SiO2N is the general formula for three-dimensional silicates. And how these silicates are generally formed? So these silicates are formed, by joining many number of silicate units, okay, in different patterns, in many forms, formed by joining many number of silicate units by sharing all 4 oxygen atoms. Here, how many of oxygen atoms are sharing here? 4 oxygen atoms. Whereas in sheet silicates, only 3 oxygen atoms among the 4 are sharing. Here, all 4 oxygen atoms are sharing with the other unit cells. So with this, it is like what? In 3-dimensionally, it was arranged. And the best example for this 3-dimensional silicate is what? Quartz. Quartz is the best example for 3-dimensional silicates. And one more thing, suppose if you replace some of the silicate units with aluminates, okay, so in these 3-dimensional silicates, in 3D silicates, if replacing AlO4 minus 4 in place of SiO4 minus 4, okay, then what we call? We are calling them as aluminosilicates. So what we are calling them as? Aluminosilicates. So these aluminosilicates only, the best example for these aluminosilicates is feldspar and geolites. Geolites are examples for this aluminosilicates. So the 3D silicates can easily converting into aluminosilicates by replacing some of the silicate units with aluminates. So this is about the 3-dimensional silicates. And the general formula for 3-dimensional silicate is SiO2N. Okay, there was no charge it. Why? Because all 4 oxygen atoms are sharing. So the generally it's a neutral silicate. They may ask you this question. Among the all types of silicates, which silicates are neutral silicates? Having no charge. What is that? 3-dimensional silicates. So other than this, remaining all are having charge over it. Okay. The last concept of this chapter, that is what? Geolites. Is what are geolites? So geolites already we discussed. Geolites are nothing but these are 3-dimensional crystalline solids. These are 3-dimensional crystalline solids or crystalline silicates having aluminium, silicon and oxygen in it. What are the elements present in geolites? Aluminium, silicon, oxygen and some trace amounts of sodium and water also present in the geolites. And if you ask your exact definition for the geolites. So geolites are nothing but, these are nothing but the hydrates of sodium, alumino silicates sodium aluminosilicates called geolites. The hydrates means water. Okay, the hydrates of sodium aluminosilicates we generally call it as geolites, and the general representation of these geolites. So the geolites generally we represent with NaO, oxide of sodium, and oxide of aluminum, that is Al2O3, and oxide of silica, that is SiO2, here X moles, and Y moles of H2. So this is a general representation of silicates, geolites. Okay, oxide of sodium NaO, and oxide of aluminum, that is Al2O3, and oxide of silicon, that is SiO2, and having X here, X is equal to 2, it's a fixed one. X value is 2, so you can write 2 here, no problem. And Y value generally it is from 2 to 6. So water molecules can be from 2 to 6. So this is the general chemical representation of geolites. Next one. Here two atoms, that is what aluminium and silicon. The two tetrahedral units, that is the two tetrahedral units of aluminium and silicon. So aluminium tetrahedral unit and the silicon tetrahedral unit. These two tetrahedral units are sharing oxygens between those two tetrahedral units. So the two tetrahedral units of aluminium and silicon sharing oxygen atoms between them. Okay, next, generally if you see the physical appearance of these geolites are generally they are porous honeycomb like structure. Have you seen the honeycomb? So there was a pores on it, on its surface. Same as like the geolites are porous, okay, but rigid. Okay, they are rigid structures. Okay, they are porous, rigid, and appear like honeycomb structures. Okay, these are the physical appearance of this. And in these pores, because of the presence of the pores on its appearance, okay, in that pores, some smaller ions like Na plus ions and a water molecule will be holded in the pores of the structure. So the smaller ions like Na plus and water molecules hold in these pore structures, okay, with weak forces, by using weak van der Waals forces. Okay, here the water molecules and some sodium ions are are holding in the pores of the structures. And one more thing, because of its rigidness, okay, we can use these geolites as molecular sieves. Okay, as a molecular sieves, we can use these geolites. And one more use of this, the geolite ZSM5. The geolite ZSM5, it's an example for geolite ZSM5. We can use this ZSM5 for the conversion of alcohol directly into gasoline. Gasoline is nothing but petrol. We can convert alcohols into petrol by using this geolite, that is ZSM5. So these are some uses of these geolites. Okay, so I hope you understand this concept. So in this video, in this part of videos, generally I discuss wholly our state board syllabus. If you wanted to any information, extra information for the competitive exams, please go through the other sources like Singage is the best material, MTG, Arihant. Okay, and also previously we already shooted some videos related to the NEET. Okay, so once after you finish watching this all, once you watch that previous videos also. Okay, so I hope you understood well. If any doubts are there, please ping me in the WhatsApp. I'll contact you. Thank you.